Hello. Today is my second lecture, and in this lecture, I will talk about the different classification algorithms in machine learning. The topics that I will cover in my today's lecture includes the definition of classification, like I will explain what is classification. Then I will discuss some of the well-known classifiers in machine learning. The first one is the k-nearest neighbor classifier. The second one is the decision tree classifier. The third one is the naive Bayes classifier. And the fourth one is the linear as well as non-linear support vector machine classifier. So what is classification? Classification is basically the process where same category objects are grouped together under certain label. So what we do, first we assign label to the data and then combine the objects which belong to its respective category or label. So suppose here is the example. There are four different categories or classes of data sets. So one is this one, second one is this one, and third one is this one, and fourth one is this one. So what we do, we first assign labels or categories to each and every class, and then group the samples under their respective category. So we combine the objects based on the category, whereas in clustering we were combining the objects in an unsupervised way based on their pattern similarities. But here we just force the objects. We teach this algorithm to group the objects under a certain category. So it is different from clustering. In clustering there is no supervision, and in clustering similar objects are only combined, but here we combine the objects under certain category. Now let's discuss about the first classifier, that is the k-nearest neighbor classifier. Suppose we have two classes, one is this one and the second one is this red class. There is a test sample and we want to find its respective class. What is its category? So what we do, we find the distance of this sample from both the classes and then arrange the distance matrix and then pick and then vote this testing sample. If it get more votes from this class, then it will go to this class, otherwise it will go to this red class. Now let's talk about the k-nearest neighbor classifier algorithm. As a first step, we load all the training data and then we initialize the k value. K value are the number of voter which decide the class of the test sample. Then for total number of the training data, what we do, we calculate the distance of the test sample from each training data, and then we arrange the distances in the ascending order and then get the top k rows, select the k rows, and then we get the most frequent class of these rows as the representative class of the test sample. So this is the brief algorithm of the k-nearest neighbor classifier. Let's elaborate the k-nearest neighbor classifier algorithm with an example. So suppose there are two classes. One is the red circle, this class, and the second one is the green square. And there is a test sample which is a blue star, and we want to find its class based on KNN algorithm. So as a parameter, we assign k is equal to 3. So this star should pick 3 voters, 3 candidates which will decide its class. Now we will find the distance of this star from each of the sample in both the classes, and then arrange the distance matrix in the ascending order and pick the top three candidates. So here when we calculated the distances, this star testing sample picked all the three red circles uh, as their nearest neighbors. So here we can see that 3 out of 3 are picked as a star and 0 out of 3 are picked as squares. So we will decide its class based on the maximum number of the voters. So all three voters are from red star. So the class of this star is the red circles. Now a question arises that how can we choose the k value? So the k value should be chosen in such a way that it should give us maximum accuracy. Uh, so if we select the k value very small, like 1 or 2, then then the noise will have higher influence on the results. It can pick the noise or the outlier as its representative. As if we choose the uh, large number of the neighbors, then it becomes computationally expensive, and also it can lead to misclassification. So normally what people do, there is no hard and fast rule, but what people do, if there are even odd if there are even number of classes, so people are selecting k as an odd value. But there is no hard and fast rule for the selection of k. It depends on the outcome of your experiments. So we need to take this k under consideration while we are doing classification using the k nearest neighbor algorithm. Now let's talk about the pros and cons of the k nearest neighbor classifier algorithm. The k nearest neighbor classifier algorithm does not require training. So it does not have training time complexity, but during testing time we calculate the distance of each and every training sample from the test sample, and then sort the distances in ascending order and pick the k neighbors to the testing sample and decide its class label. So it is computationally expensive during test time. So it cannot be applied to the real-time applications. Secondly, the testing sample need to pick its class from the training sample, so it requires a lot of memory in terms of the large data set to pick its representative sample, because we have to load the data to find the class of the test sample. It has no generalization, and it cannot be applied uh, in the huge data set, or if the dimension of the data are large. So if the dimension of the data are large, it can lead to misclassification. If the data is huge, then the memory requirement is also very high. Now I will talk about another classification algorithm in machine learning that is called decision tree classifier. The decision tree classifier is supervised learning definitely, and what it does is it continuously split the data, and in the final step it gives us the class label of what we are going to expect from this classifier. It consists of three different components. The first one is the main node. Uh, this one is the that is called the root node, and below the root node there are the internal nodes. There may be many layers of these internal nodes. It depends on the features in our data set. And the last one are the leaf node, are the classification nodes. The classification nodes are the terminal nodes that predict the outcome based on the root node and the internal nodes. Now, to further elaborate decision tree classifier, so suppose we want to find the fitness of a person. So in the root node we are first checking his age. So this is the first feature, the main feature. And if the age is less than 30, if it is yes, then whether he is eating a lot of pizzas or not. So if he is eating, so it means that he is unfit. But if he is not eating a lot of pizzas, then we can say that he is fit because he is less than 30, young, and he's not eating junk food. So we are considering him as a fit. Otherwise, if he's even um, younger but he is eating junk food, then we can consider him as a unfit. In the second scenario, if he is greater than 30, then whether he is doing exercise or not in the morning, if he is doing exercise, then definitely he will be fit. But if he is not doing exercise, then there are more chances that he will be not fit. So basically the decision tree break down the features and come and then gain the information, and in the final step it gives us the predicted class. Now I will talk about one of the most important classifier, that is called naive Bayes classifier. But before going to the naive Bayes classifier, I will talk about the Bayes theorem. Bayes theorem is important. What it does is it finds the conditional probabilities. Conditional probabilities are basically the probability of an event that is happening given that it has some relation to one or more other events. So there is condition between different events. If we want to find one event, we have to find its relation with the other events. So it is conditional. For example, we want to find the patient probability of having a liver disease if they are alcoholic. So we will use this as an example to further elaborate the Bayes theorem. Suppose A represent the patients who have liver disease and B represent the alcoholic patients. Now the past data tell us that 10% of the patients who are visiting the clinic, they have the liver disease. So we can say that the probability of the liver patients is equal to 0.1, um, and 5% of the patients who are visiting the clinic, they are alcoholic. We can say that the probability of the alcoholic are 0.05. The third condition is saying that 7% of the patients who are diagnosed with the liver disease, they are alcoholic. Like the probability of B given A, B are the alcoholic, given that they are the liver patients, it is 7%. We can say that probability of B given A is equal to 0.07. Now, according to the Bayes theorem, which is given by the following formula, probability of A given B is equal to probability of B given A multiplied by probability of A divided by probability of B. Uh, Probability of B given A is 0.07, probability of A is 0.1, and probability of B is equal to 0.05. When we put all the values in this formula, we get probability of a patient which has liver diseases, given that he is alcoholic, also is 14%. So we can say that if a patient is alcoholic, there are 14% chances that he will have liver disease. Okay, so now let's start with the naive Bayes classifier. Naive Bayes classifier is basically taking the advantage of the Bayes theorem that we discussed in the previous slides. So to further discuss or to further elaborate the naive Bayes classifier, let's take an example and see how it works. Now suppose we have a data set of different text and we want to assign tags. Uh, so these are the different texts, and we are going to take them whether they are sports sentence or they are not sports sentence. So these sports and not sports are the tags that we are going to assign to these sentences. And once we train our model based on this tagging, we can then assign tags to the new sentences as well. But the first thing we need to do is, these are sentences, and if we want to find the probabilities of these sentences uh, and and to assign tags to them, we need to convert these sentences into some meaningful information. So for that, first we need to extract important features and then convert them into a numeric form. Once we convert them into a numeric form, we will apply the Bayes theorem. Uh, the Bayes theorem is given by this formula, where it is saying that probability of A given B is equal to probability of B given A multiplied by probability of A divided by the probability of B. Now consider a sentence is given which is a very close game, and we want to find the tag for this sentence. Uh, According to the Bayes theorem, the probability that it is sports given the sentence is equal to probability of a sentence given that it is sports multiplied by probability of sports divided by the normalization term. Here what we will do, we will find the probability uh, that a sentence given that it is sports and the probability of the sentence given that it is not sports. So we will find these two probabilities. These are the likelihood probabilities, and then we will compare these two probabilities and decide the tag for the given sentence based on the calculated probabilities. But here we can see that a sentence, a very close game, is not included in our training data set here. So these are the examples of our training data set. Now how can we classify this new sentence? A naive Bayes approach provides the solution to this. So consider the each and every word in this sentence are independent of each other, then the probability of this whole sentence is equal to the multiplication of their individual words probabilities, which is given by this equation. Um, Here we know that the probability of sports is equal to 3 divided by 5, because we have total number of 5 events, and the sports is repeated 3 times, 1, 2 and 3. So the probability of sports is 3 divided by 5. Similarly, the probability of not sports is equal to 2 divided by 5, because the not sports tag is repeated 2 times. If we find the probability of each word given it is sports, so consider the word game, probability of game given that it is sports tag, so we will find the repetition of the game under the tag of the sports sentences. So here we can see that the game is repeated 2 times under the tag sports word. So one is this one, and the second one is game is not included here, so it is present here. Now total number of repetition of game is 2, and the total number of words under the sports tags are 11. So we can say that the probability of game given sports is equal to 2 divided by 11. Now we can see that close is nowhere in our training data set, and if it is nowhere, then its probability is also zero. And following this rule of independent words, when we multiply these probabilities with each other, then this zero comes, because probability of close given sports is equal to zero. So there is a problem in this approach. So how to solve this problem? uh, uh, People are using the Laplace uh, Laplace smoothing approach. How they do this? They add 1 to each and every word, so that it never come to go to zero. Now if we add 1 to each and every word, suppose here, so there is possibility that the probability may go more than 1. And we don't want that, because probability should always lie between 0 and 1. To balance out that, we divide the probability of a word given the tag divided by the total number of words in our data set. So here, when we count the total number of words in our data set, they are 14. So following the Laplace smoothing approach, now we can calculate the probability of game given the tag is sport is equal to 2 plus 1. This 1 is smoothing, and this 14 is the normalization factor. So now the probability is 3 divided by 25. The rest of the likelihood probabilities for the other words are calculated in this table. Like probability of A given it is sports is equal to 2 plus 1 divided by 11 plus 14. Similarly, probability of very is equal to 1 plus 1. So very is repeated one time under the sports tag. We can find it here. There is no very in this sentence. Similarly, it is here once, and in the last sentence there is no. So very is repeated just once. So its probability is 1 plus 1 divided by 11 plus 14. Similarly, the close is nowhere in our training data set, so 0 plus the smoothing factor divided by 11 plus 14, and game is repeated two times as we already discussed above. 2 plus 1 divided by 11 plus 14. So these are the probabilities of the words given that the tag is sports. Now we will also find the probabilities of these words given that the tag is not sports. So here we can see that A is repeated just once in the not sport tag. So no A here, and here is just one time. So 1 plus smoothing factor divided by 9 are the total number of words in the non-sports tag, plus 14 is the normalization term. Very is nowhere in the non-sports tag, so 0 plus 1 divided by 9 plus 14. Similarly, close is repeated just once, so 1 plus 1 divided by 9 plus 14. And game is repeated, there is no game word in the under the non-sports tag, so it is 0 plus 1 divided by 9 plus 14. So as a last step, we calculated all these probabilities for both the tags sports and not sports. We will multiply all these probabilities that are calculated in this table and multiply it here, and we will get the total probability. Sorry, this is not 0. This is calculated is here because of the smoothing. So the total probability of the sentence given that the tag is sports is 0.00000276. And similarly, if we calculate the probability of the sentence given the tag is nuts sports, it is smaller than the probability that given that the tag is sports. So here we compare these two probabilities, and this probability is higher than this one. So based on the higher probability, we assign the class to this sentence. And now the label of this sports, the tag of this sports, this sentence is sports. So we will give the tag of sports to this sentence. Until now, we talked about the three different classifiers in machine learning. First one was the k nearest neighbor classifier. The second one was the decision tree classifier. And the third one was the naive Bayes classifier. Now I will talk about the most important and well-known classifier in machine learning, that is called support vector machine. So before going into the detail of the support vector machine, let's pose a question. Like suppose we have this data set that consists of two classes. One is this one and the second one is this one. Now we want to classify this data set into two classes, positive class and a negative class. So how can we classify this data set? So we need to draw a decision boundary, a line, and then on one side of the line there is one class, and on the other side there is second class. But the question is, how can we draw a line? So there are many ways to draw a line. So this is also one way. On this side of the line, these are the positive example, and on this side of the line, these are the negative examples. The second way may be this line. This side is the positive side and this side is the negative side. Similarly, we can also draw this line. The upside are the positive samples and the downsides are the negative samples class. There are infinite ways where we can divide these data set into two different classes. So what is the optimal way to draw a line? So support vector machine is the answer to that optimal classification boundary. Now the best way to separate the positive samples from the negative sample is to draw a line which has maximum separation between the positive and the negative sample. So this dotted line is the line which provides the maximum separation between the positive and the negative samples. It is in the middle of these two, like not only in the middle, but it is drawn in such a way that the positive class is well separated from the negative class. Support vector machine provides this capability to divide or to classify the two classes from each other by a line which separate them with the maximum margins. But now the question arises that how can we draw this line? How can we make rules to draw this line? So in the coming slide, I will go through the mathematical modeling of how can we draw this line so that it can classify both the positive and the negative samples with maximum separation. Let's go to find the optimal boundary with maximum separation between the positive class and the negative class. Let's make a rule for this decision boundary. So what we are going to do is, first we initially draw a line, a separation line between the two classes, positive class and the negative class. And next what we will do is we will draw a vector W which is perpendicular to the line uh, that is separating the two classes from each other. Until now we don't know about the length of the vector w, and we also don't know the position of this line yet, but all we know is we are dividing we are drawing a weight vector w which would be perpendicular to the line which is separating the two classes, the positive class from the negative class. Now next step is we are taking we will take an example. So suppose here xi, we took an example here, and then we will find it that whether this example lies on the left side of this line if it is two-dimensional, or hyperplane if it is more than two-dimensional. So whether this xi lies on the left side of this line or it is on the right side, whether it belongs to the negative class or it belongs to the positive class. So we will find it using this weight vector. Now to find whether this xi lies on the right side or on the left side of this decision boundary, let's just talk about the dot product. So suppose there are two vectors, one is y and the second one is x, and we want to uh, find a projection of this x vector on y. So what we do, we take the dot product between x and y, and dot product is equal to x dot y is equal to xy cos theta. So the dot product gives us the projection of this x vector on the y vector. Why we are doing that? Because we want to use this perpendicular vector w uh, and find this xi whether it lies on the left side or on the right side. So what we will do, we will calculate, we will take this projection of this xi on w by using the dot product between w and xi, and then the result of the dot product will give us whether that xi lies on the left side or on the right side of this decision boundary. Now suppose if this xi lies on the boundary, this boundary, and when we take the dot product of w with xi, and then it will be equal to b is some constant which lies on this boundary. So this is the distance from origin to this decision boundary is equal to b. But if this point xi lies on the positive side, then the dot product between xi and w will be greater than b, because b is this decision boundary, and if it is if the dot product is greater than b, it will be considered as a positive sample. If this dot product between w and xi is less than b, then it will be considered as negative sample. Here we can see that if the dot product between xi and w is less than b, we will consider it as a negative example. If it is greater than b, then it will be considered as a positive sample. Now what support vector machine does, it forms a stream between two classes, the negative and the positive class. Uh, so like it does not divide the classes by a single line, we can say, like it will draw a line which is kind of forming a stream. So this whole is considered as a decision boundary. This maximum separation is considered as a separation boundary rather than this dotted line. So what we are going to do is we want to add some margin to the initial drawn decision boundary, this dotted line, which is b distance away from the reference point here. So we will add 1 to this decision boundary and for positive samples, and subtract 1 from this B in term of the negative samples. So if it is xi is the positive sample, we will take the dot product and it will be greater than B with additional 1 is added to the B. So if we take this B to the left side, so this will be xi dot w minus B is greater than 1. So this is the new decision rule for the positive class. And similarly, in term of the negative sample xi, previously it was xi dot w is less than B, but we have subtracted 1 to provide the margin to the decision boundary. So it is now B minus 1. We will take this B again to the left side. It will now be xi dot w minus B is less than minus 1 for the negative sample. So this is now the new decision rule for the negative sample, and this is the new decision rule for the positive sample. Now we will introduce a new variable yi for a mathematical convenience. Yi is equal to plus 1 for positive sample, and yi is equal to minus 1 for the negative samples. Considering the previous equations for positive and negative examples, we will multiply yi on both sides of the equation. For the positive sample, here we multiply yi on this side and on this side. For the positive sample, if and as we know that yi is equal to plus 1 for the positive sample, so we will replace the value of plus 1 here, similarly plus 1 here. Now when we multiply it with plus 1, the equation doesn't change. So the final equation is yi multiplied by xi dot w minus b is greater than 1. Now we will multiply yi for the negative sample. So here we multiply yi on both sides for the equation of the negative sample, and as we know that yi is equal to minus 1, we replace the value of yi minus 1 and minus 1 here, and when we multiply with minus, the sign of inequality changes, so it is less than, so here it will be greater than 1. And the final equation for the negative sample after multiplying y is equal to this equation. So here we can see that by introducing the new variable yi, both the equation for positive and negative samples becomes equal to each other. Now we can write both the equation as a single equation because of the introduction of this new variable yi. Here is the final equation. So here what we did, we just bring this one to the left side, and then we can write this equation for both positive and negative samples, which is as yi multiplied by xi dot w minus b minus 1 is greater than 0. So this is the final equation for both the positive and negative samples. Once we form the final equation for all the samples including positive as well as negative samples, what we are going to do is we will represent where the samples lie with what equation. So these lines, this one and this one, these are the margin line, and this whole is the width of the stream. The SVM will classify the samples which are on this side of the stream or on this side of the stream. Now the samples which lie on this margin line, this is the positive side the samples belonging to the positive class, they will be represented by w dot x plus b minus 1 is equal to 0. Whereas on this side, because when we put the value of yi, it will give us with this equation based on the value of yi, because yi is plus 1 as I explained previously, plus 1 for the positive sample and minus 1 for the negative sample. So if we put yi minus 1 for the negative sample, then we will get this equation and it will become 0. So the sample they lying on the margins will be represented by these equations, and this equation shows the center of the stream, because this dotted line, which is the midpoint or the middle line of the stream, is b distance away from the reference. Now the samples lying on the margins, they are called support vectors. Support vectors are very important because we will consider them as the decision boundary for classifying the different classes from each other. So we will calculate the support vectors using this equation. In the coming slides, I will explain it further. Until now, our focus was on the formulation of a single equation for the classification of a point, whether it is belonging to the positive class or the negative class. For that, what we did, we took a sample randomly and then we projected sample on the weight vector w, and then using the single equation that we formulated using the previous slides, and based on the values we decided whether it is lying on the left side or on the right side. But till now we don't know how can we form this optimal stream which provides maximum separation between the positive and the negative classes. So now how can we optimize this stream? We will now come to the point of optimal stream for classifying the positive samples from the negative samples, and in the next slide our focus will be on the optimization of the stream for classifying the different classes samples. The objective of support vector machine is to maximize the width of this stream. So to optimize this width, we want to find how can we maximize this width. So for that we need to take two examples. One is the negative example from the negative class, and the second one is the positive example from the positive class, and we want to subtract the negative samples vector from the positive sample vector. So this is the subtraction of the negative samples from the positive vector here, but this is not the width of the stream. So the width of the stream is basically the perpendicular line to the width. So this is the width. So how can we find the width of the this stream? So actually, as we discussed in our initial slides, that we select a w vector which is always perpendicular to the decision boundary. So what we need to do, we want to find the projection of this vector on the weight vector. So for that, as this is the subtracted vector x plus minus x minus, and what we need to do, we will take the dot product of this vector with the unit vector. So this is the unit vector. The vector divided by its magnitude is unit vector, and this will give us the width of this stream. As we have selected the support vectors for which the equation is this one. Now we can find the x plus dot w divided by magnitude of w, which is equal to 1 minus b. Similarly, for the negative sample, this is equal to 1 plus b. So if we put these values in the previous equation, which is width is equal to x plus minus x minus dot w divided by w, so it becomes 1 minus b plus 1 plus b. So the b and b will cancel out and we will get 2 divided by magnitude of w. uh, so for we need to maximize this equation, uh, which is equal to 2 divided by the magnitude of the w. Now we will drop 2 because it's a constant and it does not contribute. So to maximize 1 over magnitude of w, it is also equal to minimizing the w because it is the reverse. So we can minimize the reverse of 1 over the maximum of something. So what we need to do, we will minimize the magnitude of w. Now for mathematical convenience, when we take the derivative, we normally take 1/2 of the square of that objective. So what we did here, we multiply it with 1/2 and took the square of this. So when we take the derivative, this 2 will cancel out with this half. So the final equation is we need to minimize is given by this one. So this is the main objective of support vector machine, to draw an optimal decision boundary with maximum separation between two classes. And to minimize this objective, we need to use a Lagrange multiplier. However, when we want to minimize this, we need to consider the constraint also. So there is a constraint which is given as which is given by this equation. So we need to consider this constraint also, this or this one, and we will use the Lagrange multiplier to optimize this constraint optimization problem. Now this is the final objective of the support vector machine, that consists of the main objective function that we want to minimize. This is related to the width of the stream or the width of the margin between two different classes, and this one is the constraint of the support vector machine. So to optimize this, we use Lagrangian, and this one is the Lagrange multiplier. In terms of the Lagrange multiplier, we will take the derivative of the objective function L with respect to the variable or with respect to the parameters that we want to optimize. So here we are optimizing W. We will take the derivative of this objective with respect to W. After taking the derivative of L with respect to W, and then we will set it equal to 0, because the derivative at the peak is always equal to 0. So whether it is minima or maxima, the derivative there will be 0. So we will set it 0, and then after setting it to 0, we will get the values of W. Here we can see that W is basically the linear sum of all the samples inside the data set. Next, we need to find the derivative of the objective function with respect to the b. So when we take the derivative of the objective function L with respect to b, we get and set it to 0, we get the summation of all alpha I yi becomes equal to 0. So what we will do, After substituting the value of w in the objective function L, we get this equation. Here we will take out this constant outside and we will get this, and we know from our previous derivative we found out that this term is equal to 0. Now we will subtract this this part from this one, so we will get minus 1/2 of this, and this term will come down. So the final objective function become summation of alpha I minus 1/2 of summation of I and j, alpha I, alpha j, yi, yj into xi sample dot xj sample. So it is the dot product of all the samples in the data set. Previous slides we discussed that if the dot product of w with any vector xi plus b is greater than or equal to 1, then it is a positive sample. And from here we can say that if the dot product of xi, so here the w is omitted because of this derivation. So if the dot product of xi with a new vector plus b is greater than or equal to 1, then it becomes a positive sample. So this is the final objective of the support vector machine. Until now we talked about the support vector machine that works with the linear data set, where there are two data sets which is linearly separable. But here in this case we cannot divide this data set using a single line. If we draw here, then this is a misclassification. If we draw a line here, then this is a misclassification. So we cannot use a straight line to divide these two classes from each other. It's kind of exclusive OR problem. So what we need to do, we will pass this data set through a kernel, and then after passing it through a kernel we will get this kind of distribution, and now we can easily separate this into positive and negative classes. Similarly, there are two classes here. One is the outside star class, and the second one is the red circle class, which is inside the star class. So this is a non-linear representation of the data. This is non-linear data. How can we classify this kind of data using support vector machine? So if we transform this data into some other space to make it linearly separable, then we can apply the then we can classify this kind of data. So what we can do, we can use this equation x square plus y square, and when we pass this data through this equation, we will get this kind of representation, which can be easily classified into two classes. So this is a kind of kernel trick. What we are doing before classification, we apply the kernel, non-linear kernel, and transform the data into linearly separable data, and then we classify the non-linear data by transforming it into linear and then classify it there. So this is this kernel is required to classify non-linear data. That was all about the different classifiers in machine learning. Next, I will implement all these classifiers and see their results, and we will see how they behave. Thank you for now.